Everybody, welcome to Invent FM. Today we have a very special guest. Her name is Rapp, and she is a research scientist at a place very close to my heart and also close to my physical proximity, Lawrence Berkeley National Lab. Welcome to the show.
Thanks. I'm happy to be here. Thanks for inviting me.
Awesome. Yeah, we're excited to dig in. I thought that it would be helpful for some of those, obviously both of us have a connection to Berkeley Lab, and I thought it'd be helpful for our audience to just spend a quick minute explaining what is Berkeley Lab, and then what is your role at Berkeley Lab? What does it mean to be a research scientist there?
Sure. It's a big question. Berkeley Lab is a national laboratory that is primarily funded by the Department of Energy. The main goal, I would say, or theme of Berkeley Lab, when they think of Berkeley Lab as like fundamental science, sometimes it's nuclear bombs. Honestly, that's a fundamental science is correct. Weapons we don't do. A lot of our work is publicly available. And specifically what I do, which I feel like is maybe less known at Berkeley Lab, is I work in the energy technologies area, which is where we focus a lot on developing technologies to address specific problems. So it could be things like, energy efficiency standards of buildings, to developing better burners for cook stoves, some things that have gotten quite a bit of I guess front page news at the lab is the indoor air quality work we've done with looking at how does air quality from combustion appliances, or how does air quality in homes affected by combustion appliances, and then also looking at air quality in schools. So, I mean, honestly, anything from like technology development to batteries to fundamental science to policy, I mean, you name it, it's kind of all there. It's like the, I guess like, if you were going to go shopping for a science job, like you could probably find any job you wanted up there to do something in the energy space or science space. So
that's amazing. And what was your background like from a discipline?
Sure. So at the lab, I would say my main role is like I try to burn things better to help improve human health in kind of a basic way. My background is in mechanical engineering. I got my PhD at Cal in combustion, looking at alternative fuels and combustion engines. And now I feel like I've got a little bit of research ADHD. I do a whole bunch of different things, and I feel like it's hard to focus on one thing. So
But it seems like you get to do all those different things in your current role.
I do, which is one of the things I love about being at the lab, is because there's so many different projects going on that can have such huge impact. It's really fun to be able to apply the skills I have to all these different projects.
Awesome. That is amazing. So on that topic, today we're gonna really dig into one of your many projects that doesn't have to do with combustion, or at least I don't think it does.
It's thermal science. It's kind of
thermal
close.
science. It has to do with heat and heat
It's
transfer, but not combusting things,
That's
hopefully.
right.
But what I do want to say and set the stage for the live audience is, if there are questions about anything, please put them in the Q&A section. That's a lot easier for us to handle than if you put them in the chat. So there's a special Q&A section. And assuming that V agrees, I would hope that all of her different projects are fair game. So if you have questions about combustion technology, then I hope V would be happy to answer that as well. So we don't have to only ask her about this project that we're going to talk about in a second. And so that way, V, your super fans here can this is the AMA, I guess, for you, if that's okay. Are you okay with that?
That sounds great. I'm happy to answer anyone's burning questions.
Awesome. Awesome. That's amazing. That's amazing. Okay. So with that, we've got you've got a million projects. You've, in this very interdisciplinary place that, is really rooted in physics, but then actually applying those to real world problems, and using mechanical engineering, using physics, using chemistry to solve all of these things. So the invention that we want to focus on today, that I'm really excited to learn more from you about, is this infant warmer that you've been working on. And I'm curious, could you just sort of set the stage a little bit? What is the problem that this is trying to solve, right? Because this is very much applied science and engineering. It wasn't, discovery.
Right.
And so what could you set the stage with the problem statement?
Yeah. I feel like the best way to set stages is always to tell a little bit of a story.
Yeah.
Imagine you're a doctor in a neonatal ward at a hospital, and you're holding this newly born infant in your hands, and you're checking its vitals. And then you realize something's wrong. The baby's temperature is too low. You immediately recognize that the baby is hypothermic. So quickly you begin to turn around and look for anything available to get this baby warm. Immediately you spot an incubator, which seems like the natural choice because it's designed to keep infants warm, but realize that the electricity is out, so there's no way you can use it. Imagine there's the urgency and then the frustration you feel when you scramble around trying to keep this baby warm, but you don't have any of the basic resources needed to solve this seemingly simple problem. So this is how I imagine Dr. Ann Hansen, who's the founder of Global Newborn Solutions, felt when she first came across this problem in Rwanda in 2010. Each year, over 1 million infants die of hypothermia. That means 1 million babies are dying from being too cold.
That is wild.
Right?
I didn't know that.
Yeah. So you can imagine Dr. Hansen's motivation to solve this like seemingly simple problem, right? So when she came back to the US, which I should, Raymond will understand, and you guys can ask in the Q&A. Dr. Annie Hansen is actually Art Rosenfeld's daughter.
Oh, wow.
So there you go, right? Small world.
Okay.
When she came back to the US, being familiar with Berkeley Lab, and just the tidbit, Art Rosenfeld is the founder of the area that I'm in.
Energy technologies.
Energy
area.
technologies, right. So she came back and was like, Berkeley Lab, I got to partner with these scientists because after all, right, Berkeley Lab's mission is bringing science solutions to the world. So what better place to go? So the original team at Berkeley Lab, which included not myself, but Jonathan Slack, Roger Sathry, Mike Alam, and Ashok Gadgil. And I think it's important to mention all of them because they worked really hard to develop the original prototype. They were asked to create a warming device that could prevent hypothermia. Now, of course, when you have a customer who has a need, there's always like catches with us. And I'm sure through Cyclotron Road, you've done the customer discovery and interview and all of that. So
yeah,
Dr. Hansen required that the device had to be portable. It had to be affordable because this was going to be used in low resource, low income areas. So affordable being like anywhere at the aim was $50 and then at the most be $100. It had to be non-toxic because it was going to be used with infants. And then because of its cost, it needed to be reusable at least up to 250 times or more would of course be better because it would kind of increase the rate of return.
So is that, just to be clear, is that 250 different hypothermic babies go inside, or just like 250 days?
250, yeah. The idea would be uses. So as you put an infant on there, like, so 200, it wouldn't, yeah, it would be like 250 times an infant goes on there, or you cycle the device or whatever.
Got it. Okay.
Then of course, as I mentioned with the incubator, cannot need electricity to work. Right? Electricity is highly unreliable in some of the areas where she is. And then the big kicker, it has to maintain a constant 37C, which is a human's body temperature, for at least 5 hours.
Okay.
So the team got together, and after, as invention goes, many iterations, many failures, right? Many years. they finally came up with this design shown here. And let's see, you guys see?
Wow.
And so what this is this is a phase change material, which is a fancy name for wax that melts at the temperature of body temperature, that can be used with the infant that holds its temperature. And the magic thing about this is, and as scientists, many of you may know already, that when materials change phases, they hold a constant temperature until they've fully changed to the next phase. So as long as this thing is the mix of a liquid and solid, or it's a liquid going to its solid phase, it will hold that constant temperature. So then the next challenge in terms of holding it for 5 hours is just its capacity. So you just add as much wax as needed to hold it for the temperature length that you need. The design is like really flexible. So it can be used to with a baby on top of it. I actually meant to bring a stuffed animal, but I forgot. Or you can do what's called kangaroo mother care, where the infant's against the mother's chest and then you wrap it around the baby and the infant. This is hard right now. I haven't melted it. I have another one that's melted, which I'll show in a minute.
All right.
But,
sorry, just so I understand,
yeah.
You pre-melt it in, I guess if you don't have electricity, what would you use to pre-melt it in?
Yeah. So that's, I'm getting to that.
Oh, sorry.
No, you're good. It's a good question. That's fine. I know I'm slow.
Okay. No, I'm just too curious. No,
it's awesome. It's perfect. So as you can imagine, we're trying to knock off the things, right? Portable, it's portable, affordable. Well, I mean, this wax, it's actually non-toxic. Technically, you could eat it, but probably don't want to wax. Okay. It's reusable because all you're doing is melting it and letting it solidify, melting it, letting it solidify. So there's nothing mechanical that can break other than the plastic. And then how you use it is, so you roll it up like this. I know you're waiting in anticipation. Then if you grab a thermos, and fill it with boiling water, you can dump the boiling water over here and wait 15 minutes and it all melts. So the idea is you could use it without electricity by dumping boiling water over it, because almost everyone has a fire to boil water on because you got to cook.
Okay.
So
then how do you keep it from being too hot?
Yeah, so that's the great thing, is that there is a temperature indicator on here, and I'll talk a little bit about that, that tells you if it's too hot, too cold, or just
smiley face.
Yeah, or yay. So as you can see, super simple, I mean, to me, this was just ingenious, right? I always try to follow that Occam's razor rule, because usually the simplest solution is the correct or best solution. I feel like this fits to a T within that. So, great success that they got this done, right? They've successfully, the team of scientists and a whole bunch of students, because that's how Berkeley Lab stays afloat, is with help of students, successfully fabricated 12 of the infant warmers. And then they sent the mats out to Rwanda for clinical trials with Dr. Hansen. And this was in 2016, so 6 years after Dr. Hansen identified the problem. She went back and it was a really big success. I mean, over 90% of the encounters with the warmer brought hypothermic infants back to their normal temperature, or euthermia, as it's called. Wow. So with success of the team, of course, the next step was, how do we scale up and how do we get this to mass manufacturing?
Awesome. Hey, before we go into that, I just have one question. I'm just really curious. Is 5 hours enough to bring them back up to temperature, or this is a days long kind of?
Usually the 5 hours is enough. And the idea is if there's, infants, if they die from hypothermia, it's usually within the first 24 hours. If you can get them to euthermia within the 24 hours, then they're usually fine. So it's a weird, I know. I couldn't tell you why, because I'm not a doctor, but that's my understanding. It's kind of surprising.
Yeah, well, I mean, I'm not a doctor either, but I'm just, from an evolutionary perspective, it kind of makes sense that it's okay, if this organism isn't born into a supportive environment that,
right,
and the right temperature, literal sense of you know, the word environment,
Right.
like pressure, temperature,
Sure.
gas concentrations of oxygen, right?
Right.
Then I guess it just kind of makes sense to me biologically, like, okay, you know, let's like shut that down if it's not working. And like if it is working, then everything, all the other metabolisms would kick in. Again, I don't know anything about human biology, but
Yeah. I,
well, it's very interesting. I like
Yeah,
that.
it's pretty cool. And you can imagine with like low birth weight babies or preemie babies, this
Hmm.
is a huge deal. And what's interesting about infants and just kids, like smaller kids in general, is like they're really bad at regulating their body temperature because it has
Yeah.
like a mass to surface area issue,
Yeah.
right? They have a lot more surface area per mass, whereas
Yeah.
adults, we have like it's much more balanced. So that's why kids get cold easily, get hot easily, you know, and
Hmm.
then it's just their body is learning to regulate itself as it grows. So
Yeah. That's
yeah,
amazing. It
it makes
reminds me,
sense.
me and my little brother we would go into the kitchen and stand over the heater
Yeah, I used to
and
do
then like
that, the forced air heater.
yeah,
Yeah.
and then like let the hot air blow up our pajama pants
Yeah.
and just like that was our like if we were too cold, you just like run over to the heater and like stand right,
I
right
remember
out.
taking a blanket and just like camping out there all winter. And so, because I grew up in Utah, so you know, during the winter time, there's lots of snow, and so it's just like I'm just going to stay on top of this vent. And then when it stopped, I was always disappointed. It's like, where's the
Yeah,
hot air?
right.
So, yeah, nope, I get it. Cool. So, like all stories, right? There's all these ups and downs. So, great success, but now here's where things get a little
Oh,
complicated, always, right? So, because I feel like, you know, everyone's like, oh, innovation, you know, they made this product, it was like super easy, everything went smooth, nothing went wrong. And it's like, no, absolutely everything goes wrong. And you have all these hurdles that you have to keep jumping. And it can be exhausting if the hurdles keep coming. So the idea is perseverance, right?
okay.
So the first original 12 mats, as I said, were made by scientists and students by hand. So this is what we call a candle. That was one of the things inside of here.
Okay.
Um, if you think about like how you're a material science, you understand materials. How would you make this by hand?
Uh,
So got the little candle here.
and I get no tools.
No, I mean, you're at the lab, right?
Oh,
So
I guess uh I would have one open end. I'd melt the wax, pour it in, and then seal the other end. I don't know, or
right.
vacuum seal it. I don't know if I had that.
Right. So if you vacuum seal a liquid, what happens?
You got no, you got bubbles.
Yeah, bubbles and like it comes out, you can kind of see, right? So
Oh, so
you can
yeah, you put that on a vacuum sealer, and the bubbles got in the way, or the
yeah, well, so then
material
you
started getting sucked out.
sucked out, but then if you don't leave enough room, like so this is the magic thing about water, right? Water when it solidifies, it expands, but everything else,
Yeah,
right?
it's one of the
Like
only things that does that. Yeah.
yeah, right. So like, you know, you got to leave a little wiggle room so that we don't expand,
Okay.
contract, right? Like the plastics and all that. So needless to say, what you've described doesn't sound very easy to do by hand. That is basically what they did. It's a mess because this solidifies at body temperature, right? 37 C. So like, as you're trying to work with this in a room, right? That's colder. It's
Yeah.
solidifying quickly. So as you can imagine, the success rate of building one of these mats by hand was 15%.
15% yield. Okay.
15, 1 5, right? So
Yeah.
85% of the mats made by hand did not meet specification and couldn't make it out to the field. So if we're trying to scale up, this isn't a viable option, right? It's also really expensive because you're paying scientists and students to like do this by hand.
Mm-hmm. Yeah.
The other catch with this, right, for scale up is because we were trying to meet like deadlines so Dr. Hansen could like take this out into the field and try it out. There were some decisions made that resulted in higher costs. And one of them was this really cute temperature indicator.
Yeah.
So this indicator, it's what's called a liquid crystal temperature indicator. So this is like, it's embarrassing, but The only thing I can think of that like might be more relatable to people is, when you like pee in a cup for the doctor, there's like that little indicator. It's the same technology.
Okay.
So, to tell you what temperature.
Yeah.
So they're designed to kind of be like one use. They're not reusable, and these are $5 each. So if this mat's $50, that's 10% of the cost.
And it's
So
not meant to cycle
it's
overnight.
not meant to cycle. So there was a big issue with these cost a lot, and they don't cycle. They last a few cycles, and then that's kind of it. So we
Okay.
needed to figure out a new solution for this indicator. So knowing that like I have a huge passion for solving problems, especially when it comes to like human health or improving human health. Dr. Ashok Gadgil, who was on the original team, asked me if I would come help advance the infant warmer for scale up. And this was in late or maybe early 2016. I forget. I don't know. Time is weird right now.
I have been having the same experience of a complete distorted sense
Right.
of how long things take.
For sure. Yeah. So, at that time I was a new mom, so even more fuzzy brained in terms of time. But as a new mom, like, I mean, how could I say no, right? Like the thought that I could help a woman at this most critical time and most critical moment in their lives, right? And give them a chance to watch their child grow. I mean, it was instinctual. Of course, the answer was yes. And
Yeah.
of course, like all projects like this, right, there was very little funding and there was a very short turnaround time. So let the races begin.
Yeah.
So of course I took on the project, even though it was outside my main field of expertise. But for some reason, I have this knack for tackling problems with short deadlines, right, that need to get pushed out, and so that have impact. And so I was ready to go. So of course, I started with interviewing Dr. Hansen to do a little more customer discovery to figure out like what were the main issues that they had with the warmer. What did they like? What did they didn't like? So that I can understand from the original design as we brought it up to manufacturing, what we should keep and what could go, right? And specifically around this, that liquid crystal temperature indicator.
Okay.
So that helped me identify what we needed to be preserved and what we could toss for the automated manufacturing. And before I tried to seek out a manufacturing partner, I knew I needed to kind of figure out the indicator first, because that was going to be a part of the manufacturing process. Like, when does it get added in, right?
Mm-hmm.
So I spent, oh my goodness, I think I spent like months trying to find an indicator, only just to discover that like there was nothing off the shelf that was cheap, that was reusable, that was reliable, that worked right around body temperature. So I began to think about, how can we work around this issue? And oftentimes when I get stuck in these kind of loops where it seems like, there's no solution, I often will revert back to like the most fundamental question. And in this case, it was, what is the temperature indicator's purpose, right? Like, what is it supposed to do? Right.
Mm-hmm.
And so I began thinking about that and talking to Dr. Hansen a little more. And it became really clear that the indicator's main purpose is to ensure that we don't burn babies, right? To show that the mat is not too hot. And I was like, okay, well, that simplifies the problem a little bit, because I don't have to necessarily worry about like, is it too cold? And honestly, when this thing starts to get hard, it's pretty clear like that it's getting cold. So
Yeah,
that helped.
I was gonna say it seems somewhat self-indicating,
Right?
at least on the low end of the spectrum, right?
Right. And then, I think I also got hung up because like she kept talking about like you said, the cute little smiley face, right? It's like Goldilocks. Is it too hot, too cold, or just right? Right. And of course it's a great indicator in the sense that it is very clear like what the issue is, right? That it's too hot, too cold, or it's ready to use, which is
Mm-hmm.
really key. If you're in a hospital situation, you don't really have time to like figure out what the heck does that symbol mean, right?
Yeah.
So it made it really, really fast. So I began to brainstorm some ideas with Ashok. after not a whole lot of success, we decided, okay, let's start tackling a few other problems. And then I think during a phone conversation when I was testing plastics for this warmer with him, it like dawned, I don't know, it was sort of an aha, but I think really like, I feel like when you let problems stew in the back of your head and then take a break from them, it's kind of like they work themselves out. So whatever it was when I was cooking plastic on my stove, something triggered and we started talking about, well, why can't we use the phase change material as an indicator? Exactly like you said, right? It seems self-indicating. So what if we just had another phase change material that changed phases at a higher temperature and use that as our indicator? And it's reliable and it's cheap and it could easily be integrated in the manufacturing process. So that was kind of our ideal solution. So that was what and interestingly, someone said, well, you should patent that. And I was like, someone has thought of this before. You got to be kidding me. Like, this is like really seems simple, right? And so I started looking around and I couldn't find any patents on it. So we filed a patent, and that's kind of what led to the Patents of Humanity honorable mention. So that was kind of cool.
That's amazing. That's so cool. Can you tell me, well, one, I'm just curious, what is the Patents for Humanity honorable mention?
So Patents for Humanity it's the US patent, it's PTO, patent something
Patent and
office.
Trademark Office.
Yeah, trademark office. Thank you. I'm terrible with acronyms. So they have a Patents for Humanity award that is inconsistent. Sometimes they think their goal is to have it every other year. It doesn't always happen depending on funding. But the idea is to highlight technologies that have had impact on humanitarian efforts. And it was really a big deal for us because we were with people who had like developed these amazing drugs to solve all of these like horrible diseases, and people who had developed these technologies to solve, all of these other problems. And so it felt like, I don't know, kind of cool and also kind of intimidating to be like up there kind of with all of these other people who have done all of this really amazing work, right? So it was pretty neat. So
that is amazing. Congratulations.
Yeah, thanks. So of course, after solving the indicator problems, right, our problems were not all solved, right? We still needed to find a manufacturer. So this was really hard to do. I'm not gonna lie, like it was a lot harder to find someone to manufacture these, because immediately when I first saw these, I was thinking, oh, Otter Pops, or like,
I thought the exact same thing.
like Go-Gurts or something, right?
Yeah.
And I'm like, why can't someone just like, I'm like, just inject them and like seal them? I don't get it. Well, this goes back to the wax goes hard at 37, right? Go-Gurt and Otter Pops are going to stay liquid. Also,
until you freeze them.
Until you freeze them, and you're not going to cycle freeze them. So the plastic you use matters, right? Okay. So like, you're not going to take Otter Pops and like drop them in boiling water and pull them out, and drop them in boiling water and pull them out, which I learned a lot about plastics after this. I have yet,
the great joys of durability and weathering testing.
Yes, and sealing. Cycling. Yeah, so I learned that there are very few plastics that can handle boiling water while maintaining their seal, right? Almost all of them, like their seal temperature is, and non-toxic and doesn't react with the PCM. So, because it's organic. Yeah. I learned all sorts of new challenges through this. But needless to say, after over a year, and it was by sheer coincidence, we finally found a manufacturer. I was reaching out to a company actually to have them custom make the phase change material for the indicator. And she says to me, oh, I read this really cool article with Dr. Hansen. Are you like working on that? And I was like, no way. I'm like, what article? And so she shared it with me. I was like, I had no idea that even came out. And she's like, that's a really cool like technology. And I was like, oh, I'm like, well, since you're in this space, I'm like, do you know anyone who has a machine that can like handle all of these, challenges? And she's like, oh yeah, so we just actually bought a machine. She's like, we might be able to help you out. I was like, oh my gosh, this is like too perfect, right? And of course it's, 10 months before we're supposed to have this thing produced. like 500 of them manufactured so that she can take them to the field to like do a bigger study.
So sorry, just so I understand, is the machine just a fancy vacuum sealing or lamination to what it sounds like?
Yes.
If they bought it, it's not the machine that seals these things itself isn't like an invention, so to speak, or like had already existed in the universe. But
Right.
so what was the manufacturing tool?
So it's like a giant sealing machine. It's like an giant injection sealing machine. So
Okay, cool.
I think often those machines are used for making like those reusable ice packs.
Yeah,
Right, that have the little square pouches.
right.
So it's a machine that like, forms the plastic, because the idea for us is we wanted this to be fully automated, right? So you can actually produce 500 of them easily, and then maybe 1,000 or 10,000 or whatever.
Okay.
And so this machine kind of like it sort of fit the bill. I think there were some things that needed to be all modified, right, in terms of the die cast, and then we needed a plastic that was going to work with it. And then the other unique thing is this company also had, so the wax comes in like a 50-gallon drum. And melting wax out of a 50-gallon drum is not exactly like trivial. So apparently they are one of the few that have a machine that, like, I haven't seen this. I was really hoping to go out there and see the whole thing. But it actually heats the drum to get the wax into liquid form so they can get it out. Yeah, I think so. And I was imagining, like, I mean, those things were heavy because they came to the lab and then I had to like ship them there. Really heavy. So
I will
yeah.
I will not go into the story of trying to get 55-gallon drums of organic materials delivered to Berkeley Lab during my
I did
time.
it. I had 3 of them.
Yeah, I tried for a few years, but didn't work out. But yeah, that is yeah, it's those really simple things that, like, on, as a chemist, right, like you're like, oh, on this scale of this little vial,
Right.
it's like, oh, whatever, I put it on the hot plate and mix these things together, and then and yeah, there's lots of I won't go into ours, but there's lots of materials that I worked with, both at Cypress and at Polyspectra, where yeah, it's like, this will be liquid for a little while, but depending on how long it took from going from the 55-gallon drum from the factory to you, it might be solid when you get it. It might be turned solid the day after you open it.
Right.
And chiseling wax out of a giant drum isn't the way to go. So
nope. And good luck using sheet metal shears to pry that thing open. So
oh yeah.
I mean, not that I ever would.
Yeah, not that anyone on my team or myself has ever
never
torn open a can.
No idea what you're talking about. So yeah.
Safety first at Berkeley Lab.
Yep, exactly. Always. I will add as a kind of a
and
fun
at Polyspectra,
note, right?
For the record.
Yes. I will add that was kind of fun is when those 3 drums showed up, because I run the combustion lab. The immediate question I got for safety was, what is in there? Is it flammable? Right? You can't have 3 50-gallon drums of flammable material. I'm like, so there was a lot of explaining of it's not flammable yet, because it is wax, right? Like, I'm like, I'm not using it to burn things. It's solid. For some reason, it being solid.
Although I am a combustion expert, I do not plan to combust this material.
Exactly.
That's amazing.
Yeah. So
despite your credentials.
Right, exactly. I promise you I'm not burning the wax. So yeah, so we worked with a manufacturer. I mean, I'll spare a lot of details and let people ask questions, but we finally got something made. And one question I wanted to ask you, because this was kind of another fun thing, was if you were to make a temperature indicator that was to indicate something was too hot, what color would you make it? These are the kind of things I feel like as engineers we don't really think about very often.
Want it to be red or orange when it's too hot.
Good answer. So originally I had picked red because to me instinctively red means hot, don't touch, right? So we made them red. We had 10 of them made, and we sent it to Rwanda. We sent them to Rwanda, and immediately the nurses go, "Is there blood in there?"
Oh my God.
So I'm like, "Oh yeah, that's right. It does kind of look like blood." And so we immediately had to change the color. So good choice. We went with orange. So this is the indicator. And this is the matte warm, so you can kind of see. So I'm gonna try not to drip on my computer because it was in the water.
Oh wow. So each rod has its own little
Right.
pocket.
So originally,
I love that color. It's like very close to my heart.
Right. It's an awesome orange. So originally we were going to do one candle that was the indicator. For manufacturing reasons, this is where we landed. So as you can see, it's like super flexible. Sorry, I'm going to like drip water all over me.
That's
right.
okay.
Actually, I wish I could like hand it to you so you could feel it. It's really warm. It's nice and cozy. I kind of want to just like wrap it around me right now.
That's
so,
amazing.
and it'll stay warm for like, anywhere from 5 to 7 hours, depending on like if it's laid on a really cold surface.
Okay.
And so
I'll get a bike messenger to bring it from where you are to me, and
sounds
I think
good.
it's less than a 5-hour bike ride.
Sounds good. So a few questions, because I'm mostly just showing you the mat that I know I'm probably going to get here is, do babies really lay on this and it's going to get hard, right? It's going to get to this at some point. Okay. No, they don't lay directly like on this. There's actually a sleeve that has instructions as well as like a foam pad in it that this slides into. So like there's a pocket here and you slide the mat in. And then this gets wrapped around the baby. So it's nice and cozy for the babies. So no, we're not making infants suffer on a hard surface when this thing gets hard. And then all of this is portable. So the idea is the kit is like this with the mat or with the sleeve with the thermos in a backpack. So even like a midwife going to do home deliveries could take it with her. So wow. And I'll leave this out and you'll see it's starting to kind of cloud, right? Can you kind of see it?
Yeah, a little bit.
Yeah, so you can kind of see a little bit of the crystals because it's starting to solidify. So this changes temperature at 40, I think, C, because that was kind of what the temperature that Dr. Hansen wanted. And then the rest of this is like 37. So
okay.
I'll leave it at
sorry, so the definition of Goldilocks zone is the orange one is solid.
Yep.
But the clear ones are liquid.
Are liquid, right?
So then you're supposed to like feel them all and make sure that they're okay.
No, so they'll go, instead of being nice and clear, they'll go opaque, right?
Oh, so it's got it.
Right, it'll eventually turn to like this.
Oh, okay. So the color also will go away, and then you'll see that, and then you'll stuff it in the bag, and then you'll wrap the baby.
Right, exactly. So actually, the nice thing is the bag has like a little cutout.
A window.
A window, yeah.
Oh, that's great.
Right, so let's see. As I struggle with this thing,
that's okay.
So not a trained nurse to stuff this thing in here. So, but yeah, the idea is that it has the window, and then as soon as the orange piece kind of goes opaque, which it still stays orange. It's just it's not clear anymore. And also it does, as you said, it gets physically hard, so they could even push it. Then it kind of tells them, okay, this mat is definitely ready for use. And in all honesty, even the 40 won't like, so you can kind of see.
Oh, cool.
Right. And it's actually like, it's there. I mean, it cools fast. So you can kind of see now it's not clear anymore. Right.
Got it.
So, and it's pretty hard. So yeah. And then
that's ready to use. Not gonna burn a baby.
Nope. And truthfully, wouldn't burn a baby before anyway. So
okay.
It's we designed in a few extra safety factors in here. So yeah.
Got it.
So that's the design, right? I mean, it's it seems simple. There were so many challenges along the way. And we got through them. And despite the pandemic, Dr. Hansen got 500 of these. She brought them to Rwanda at the end of last year and was able to get through her clinical trials just recently. So those just wrapped up the second round with the new mat design. Wow. So we'll know more about the, you know, what other design optimization we need to do before we can start making, you know, thousands or tens of thousands of these things. And
That's amazing.
yeah, and so now Dr. Hansen has her nonprofit called Global Newborn Solutions, and they've officially named this the Dream Warmer.
Dream Warmer.
The Dream Warmer.
Yeah.
So
cool.
she, you know, is continuing to kind of push this forward and put this out into the field, and it's so great to like be able to use my problem solving skills to have, you know, this direct impact on the lives of women and children who I might not ever meet, but knowing that, you know, they're going to get to watch their kids grow up. So yeah, that's the project in a nutshell.
That's so beautiful. That's amazing. I can just see you light up when you
no,
say
it's
that.
fun. It's been a challenge. It's one of those weird things where it's like, it's really hard, but super fun, right? And there are some days you're like, why am I doing this? And you're like, that's right, babies.
Yeah. Well, and I think that's, I mean, to me personally, I think that is that idea of falling in love with the customer is something that it's really critical to getting out of your head, getting out of like taking all the failures personally,
right?
and something that I can really resonate with. And I think that, you know, for me, over the last few years, I've kind of, you know, so like Polyspectra was like, you know, my invention. I started this company based on my invention, that like it was my moment of discovery, and I had all these ideas for what to do with it. But then I think that we realized over the years, though, like, okay, actually what's more fun, I mean, yeah, so it sucks, things don't work, we're years behind where we thought we would be in terms of the like timeline. Things that you think are easy are really hard. In some ways it's good that they're really hard. There's invention there, right? Like your moment of like, is this really a patent? And they're like, no, it's not only a patent, it's a patent that won like the Patents for Humanity award from the freaking US Patent Office. So you know, I think that's another thing, right? Like there's value. If it's really hard, it's a really valuable problem, and if it's really hard, it's worth doing. But connecting to that mission, and that like, yeah, I'm a mom and this is the experience I want other moms to have that I might not meet, or I'm an inventor and this is the experience I want other inventors to have when they can see their thing come real. Like that for me has been it's not that, I don't know, I feel like in the last couple of months I've kind of chosen to go there more often, and I think it's been really like motivating for me, and it's less like striving oriented and more like fun.
Yeah, I agree. I think it's good to focus on the like, why are you doing this, right? And I think one of the fun things about this project and probably why I enjoyed it so much is kind of like you said, there are other technologies I've worked on where all of a sudden they become my own, right? Like it's like I'm married to this technology and it's like my baby, right? And I'm just so connected to it. And if it fails, I feel like I'm failing. But you know, in this case, it was really kind of a nice project to work on because this wasn't like my project, right? It was so easy to just go, oh, that design didn't work. Okay, next, right? And instead of being like, no, I have to force this specific way that I've thought of this to work. And it was incredibly freeing. And I think that experience made me realize I really need to like dissociate my emotions from the technology. The technology is the technology. I am me, right? If the technology fails, it doesn't mean I am a failure, right? I think the entrepreneur line is businesses fails, entrepreneurs don't, right? They keep going, they continue being entrepreneurs.
I like that.
I was like, oh yeah, that was advice I got when I went through LabCorp. So, and I was like, it's true. Like things fail, devices fail, people move on, right? And so kind of keeping that mentality and it was just really freeing because it allowed me to sift through ideas a lot faster because I wasn't married to having, one specific thing work. And I think that made it easier in some ways to overcome the hurdles and also keep my eye focused on the why, right? Like this is why I'm doing this. And it made it a lot more fun. So
That's amazing.
Yeah.
Yeah. I love that. And then how could you learn without failing?
Exactly. Right. Yeah. You absolutely have to fail. So it's a part of
Right.
the whole process.
Yeah. Yeah. One of the things that I would often, the pieces of advice I would give to in particular like first and second year grad students that are, just about to take on this, multi-year problem or problems where it will never end.
Right.
And every problem that you solve will create 10 more problems to solve was, and it's hard and to do this, but basically my advice was, okay, you need to find the way for yourself to, to the greatest extent that you can, decouple your emotional happiness from the experimental outcome of the thing that you're doing right now.
Right.
And you have to have this, you have to have the thought that, oh yeah, the next one will work, right?
Right.
Like you can't like if you lose that, then you need the excitement and the momentum, and you kind of need to have that distortion of reality where
Right.
you just are convinced that the next one will work, and at the same time when it doesn't, you can, if you get so grumpy about that, then you're kind of blind to like, well, what could I learn from, like, this
Right.
didn't work, and like why, and what what could I learn from it.
Exactly.
So
Yeah.
yeah,
You end up
it's
kind of
really,
stalled. Right. So,
uh-huh, yeah, yeah, it's beautiful. And I think there's just, I couldn't help but, maybe this is a little cheesy, but I couldn't help but think about, so one of the questions that I am trying to answer through the process of doing Invent FM is like, what is invention? And I just had this moment through hearing you talk through the inventive part of uh, thinking, well, you're working on these phase change materials, right?
mhm.
And then and you explaining, oh, this, I didn't sort of go down and, write out all the equations and then come at this answer. I was like thinking about this for months. It was in my body, it was in my subconscious, and then you had a phase change. Right?
Yep.
And your phase change was, oh wait, the phase change material can also be
Right.
the indicator, right? I don't know. I just think there's something so beautiful about, like, it's Occam's razor, right? In that you use the same principle twice in the
Right.
design, and it's also like this meta phase change of like V had a phase change.
Yep. Yeah. I feel like oftentimes when I feel like I'm in a rut with trying to get a technology to work out or overcome some challenge, the best thing I can do is just like walk away, right? Like go for a run, do something else. Like I really like to sew. So, I'll work on different crafts or things like that. Just something that is completely different than what I was doing. And then I find that like, I don't know, when you were a student, did you find like, if you had a problem you couldn't solve and then you'd sleep and the next morning you'd be like, oh, I totally, like, I think I know how to solve this. Your brain is working in the background. Don't push it, right? Like,
Yeah.
don't, the more you force it, the more like at a standstill and like the gears will grind to a halt. So I feel like it's always good to just, take a step back and take a breath and just like, go do
Mhm.
something else for like an hour. Go take a shower, right? A lot of people talk about like their greatest, ideas come in the shower. I don't know. So just,
Yeah, Archimedes' bathtub, right?
yeah, exactly.
Uh,
Right.
but no, I think there's something beautiful about that, and I think that one of the common pieces of advice of, let's say top performers, so to speak, in the physical sciences, and one of the pieces of advice my dad gave me when I was a student was like give your subconscious homework, right? And
Right.
like whatever, if
Exactly.
it's like a problem set, you know read it like as soon as you get it,
Right.
and you might not even realize that you're working on it, and then when you have time to go do it, you've already started, right? But
Right.
if you only read it for the first time when you sit down to do it, you're not taking advantage of that. And I know lots of people like, oh, what's his name, the super famous chess prodigy who's the subject of the movie Searching for Bobby Fischer. Anyways,
Oh yeah.
I forget his name. I'll think of it as soon as we hang out. But he would like basically like every night he like before he goes to sleep, he's like, this is I'm gonna like wake up and like before he reads any text messages, looks at the news, reads the newspaper, anything, it like wakes up and like writes whatever, you know, the answer, whatever comes to him about the sort of problem he gave his unconscious. So maybe that's a little more structured than you're talking about here, but I think it is a really powerful aspect of invention
Right.
that people take for granted is, you know, in some ways these things you need to focus your conscious attention on it to set the intention for the problem. And it's not that you're not thinking about it, but also like let it permeate you in a different way.
Let it stew, right?
Yeah, I love that.
So one thing that I thought was interesting, because I know in some of your past interviews you were talking about like, what does invention mean? Given
what does it mean to you?
Well, no, so I thought this was interesting because like, okay, so I mean, I just admitted I totally cheated because I watched all your other episodes to get some ideas.
That's not cheating. There's no right answer. We're building on the shoulders of giants here. Sure, this is science.
Exactly. Right. So the thing that I found really interesting was Anna Maria's dictionary definition, right? Which of course I had to look up again about invention being the creation of something, right? A device or a process that's unique. And to me, what I found really interesting about that was it doesn't say anything about solving a problem. It just says you're making something that's unique, right? So like, I feel like, yeah, I could make something unique. It probably would be it could be totally useless, but it is an invention.
It's true.
So I thought like, for me, like maybe like, that's why I've never really felt myself as an inventor, right? Maybe I always viewed myself as like a problem solver, right? Like I like to dive in and solve problems. So maybe like it should be problem solving inventor or innovator or something like that.
There you go. Problemsolver.fm.
Sure. Invent.fm sounds much better. There's got to be, you know, don't let my engineering ruin your great title.
Okay. No, I love that. And I think, yeah. And I also, yeah, part of the fun of it is like, what does this word even mean? You know, and so I think that it's fun to, like Danielle was like, I don't self-identify as an inventor. I self-identify as a synthesizer. And I'm like, well, that's awesome. And that's, you know, that's even more fun.
Right. So. Yeah, the language part of this it's fascinating how it's like it can be freeing but also bounding, right? In terms of how we define it. So yeah.
And there's an ineffability to invention or discovery where, you know, all of these metaphors, the phase change, the lightning bolt, the light bulb, the bathtub, you know, aha, the eureka, right? It's all you know, it's pointing in the same direction, but none of them can touch the ineffability of that experience. Right.
And also the length of the process, right? Like I read a great book early on when I was feeling a bit discouraged, I think called The Myths of Innovation. I don't know if you've read that one. It's great because it goes through and basically in a nutshell says that, you know, as a society, we love hearing these like these like little anecdotal stories, right? Like a lot of people, I mean, I think engineers and scientists, many of them know already that Thomas Edison did not invent the light bulb, right? He invented a process for mass manufacturing a light bulb, and an industry for it. But the light bulb itself was invented entirely by someone else, at least the working light bulb we use. And, but yet there's this story of like, and then Edison like had this idea and the light bulb came on, right? And it's like, you know, no, that's not what happened. He made like, what was it, like 1,000 light bulbs by hand with different filaments or something ridiculous like that. And like, and none of them worked. And even at the end of the day, like he still didn't find the right filament. Yet he was able to like, you know, create an industry to get electricity to the White House and things like that. And so I feel like that book was great because it was like, and it even talked about Steve Jobs's like process to getting to like Apple and the first iPhone. And I love that at the beginning, it was like, no, he failed, and people outright rejected him. And they were like, no, this is silly. You know, you're never going to get this idea through. Nobody's going to want this. Right. And I'm just like, and, you know, I mean, it was over a decade, he was like working on that. And
Yeah.
I think it's important to recognize, like, you know, it's not like one night I was, you know, thinking about this and the next morning I was like, oh yeah, now I'm going to do this. And my whole career changed. It's like, no, it's like over 10 years, like I worked on this, like even this infant warmer, right? Like Dr. Hansen's recognized this problem in 2010. It's 2020, right?
Yeah.
I mean, and we're still not there like to mass manufacturing, but at least we have a technology that helps.
That could do it. Yeah.
Right. But it takes time. And I think giving ourselves the space to recognize, you know, I mean, I'm a total instant gratification person, so I get it.
Yeah.
But yeah, taking the time to say, okay, you know, this is going to be, I'm in it for the long haul. And it's not going to be solved overnight, but it'll be fun the whole process. So
Yeah. And on the Edison thing, I'm gonna get the numbers wrong, but Ilan Gur has a really fun presentation on this where he shows that, yeah, not only was it not overnight, and that, you know, there's lots of debate around, you know, he didn't invent it for the first time, right?
right.
And there's lots of things he stole from Tesla, and there's all
Yes.
these great stories about it. But even just for the part of him making it real, he had to start something like 7 subsidiary companies
Right.
to, like, one to make the filaments, one to run the installation company to actually put it in the wires in the ground, all this stuff.
Right.
And if you look at his original business plan, he went something like 200 times over the original budget.
Yep.
of
He was a
what
true
he,
businessman.
of what
Yeah.
he thought he needed to achieve it. And you know, anyways, it's a really fun, I want to get Alana on here to tell that story, because it's a really fun one, and he does a good job doing it. But it's important to remember that things are hard, and really valuable things are even harder.
Yeah, definitely.
And yeah, in my mind, I think that's kind of part of the, you know, if you're going to commit to solving hard problems, it's also like a personal commitment to being in it for the long game, right? You know,
Exactly.
you just don't bring a new material to market really much faster than 10 years, right? There's a lot of value once you get going, right? But that's just the reality of scaling these things. It's amazing. So hey, okay, so one, I'll just take a quick break and say, for folks that are live with us, we would love to hear your questions. There's already a couple coming in the Q&A. Please feel free to put them there, and we'll get to them very quickly. But before we go into the Q&A, V, I just want to, maybe you kind of hinted at this, but I just want to ask again, to restate. So where's the project now? So there's like 500 that those have been used for clinical trials. There's still some data to look at to make sure it's safe, or, you know, what are the next steps in this to saving the 1 million babies?
Yeah, so the to be continued, right? So right now, the clinical trials in Rwanda did just get wrapped up. The data has been synthesized, and she's working on a paper. So hopefully that will get out. Once that's out, that should, it's funny, there's all these moving, like you said, like, I mean, this was a huge team effort. I mean, not just Berkeley Lab, but also like Boston Children's Hospital, Rwanda Ministry of Health. Like, I mean, there are so many moving pieces, and I only discussed the technology. I didn't discuss, like, when it comes to medical devices, getting those approved for use in hospitals is a huge hurdle. It's hard, really hard in the United States, which is why a lot of the equipment looks archaic from the 70s. In, you know, Rwanda, it was their hospital, their structure for their hospital system makes it a little bit easier, but still there were things that were equivalent, like FDA approvals and, like, you know, using human subjects and things like that. So in order to get over some of those more like bureaucratic policy, safety, efficacy hurdles, on targets. The results from this study needed to be published before we can say, okay, this device really for real works. So now we can scale up further. So she did, there weren't as many, what she calls as encounters, which is like instances where the baby was put on the warmer and then brought like, brought to temperature, for lack of a better way to express it.
Recruitment wasn't as high as expected.
Right. And that was because of the pandemic. Like the fact that she was even able to do as many tests as she was, given the limited hospital staff and everything else that was going on, was like, is a testament to how much of a driving force and amazing she is. But it should be enough to kind of meet the bar to say, okay, look, this is a bigger study and really it does work. And so once that's out, then the next thing becomes, how do we scale up even further? And I think, we're going to reevaluate. We're going to have to understand a little bit more about what did the nurses find, like, what did they like, what did they didn't like? This is a similar process to kind of continue refining this. And then also maybe refining the design so that it can, we're not producing 500 of them, but you could manufacture, thousands of them. Because the company we were working with, I mean, they have a machine, right? So they can make 500, but that's probably it. So
you have a sense. I'm sure there's some locality to where this could have the biggest impact. Do you have a sense of, like, maybe not to get to saving all 1 million babies, but like, would you need 500,000 of these to save 500,000 babies a year? Or do you need 10 times less or 200 times? Because that's the goal, to use it 200 times. Do you have an order of magnitude?
My impression is that, like, the idea would be to get this to the thousands level. I'm not sure. I honestly don't have like a good sense. I know, that she would love to kind of get these into all the hospitals in like Rwanda, right? And you figure if they do last 250 cycles, and she, I can't remember how many infants she had on them a day, but let's say you had 10 cycles a day, right? There is going to be a lifetime on this thing where it will need to be like replaced, right? So I don't think you could be like, I made 10,000, done. Right.
But maybe 10,000 a year could save 100,000 babies a year, or I don't know.
Exactly. Something like that. And then, unsurprisingly, like majority of those million deaths from hypothermia ish, right, or over, are concentrated in places where hospitals have lower resources.
Right.
So.
Okay. Wow. Well, that's amazing. So cool. Yeah. All right. So as we kind of gear into Q&A, some final Q&A, you hinted at something that I told you I'd ask you, and then I didn't get a chance to ask you yet. But I would love to, to me, this is a very clear success example of, a public-private partnership, of international and interdisciplinary collaboration, right? With all these different organizations that all have their different business models, for lack of a better word, incentive structures, right? Some people, online are trying to save babies. Some people are trying to get tenure. Some people are making sure that they keep the DOE happy. And so I'm just, I don't know, what went well there, and what advice would you have for inventors, engineers, designers, synthesizers that realize they need to collaborate to be successful? How can they set themselves up for success?
So, I mean, I feel like I got like, I don't know. I mean, one of the perks of working at Berkeley Lab is because of the diversity of expertise and backgrounds. Like, you get to know, I mean, like, I didn't know anything about particle emissions when I first joined the lab, right? Oh, hey, guess what? The guy who happens to be an expert in particle emissions works, like, his office is 2 doors down from mine, right? So I asked him to go get a cup of coffee, and because he's like very passionate about particle emissions. He has no problem telling me everything like about particle emissions, which is great, right? I mean, working with so many people who are so passionate about what they do makes it really easy to like to work together. So I think having a diverse team is absolutely critical, because like you're never going to be the expert in everything, right? You're going to need someone to complement where you're, I mean, not to put it negatively, but where you're deficient, right? Yeah. So you have to, I mean, so I think just accepting the fact that like we all need help and it's okay, is a good way to start. When it came to this team, because it was so huge, this is where I feel like it's really critical to have like a champion, right? Like the infant warmer is not like my sole project, as you know, right? So since I am just kind of a, you know, I'm helping support, I can't champion like pushing it forward. So having Dr. Hansen like be the champion, be the voice to just be like, we are going to get this done and this is how it's going to go. It's almost like a program manager to a degree, but she kind of, you know, she was the driving force. It made it a lot easier to figure out, okay, this is what's needed. And then this is what we need to solve by this date, right? So I could focus on the technical challenges with the warmer, while she had other team members focus on the, okay, how do we get into Rwanda now that the pandemic has started? How are we going to coordinate? Like, how are we going to train the nurses so that they know how to use this new device, right? How are we going to figure out like things like the instructions so that they're really easy to understand so that nobody can mess this up, right? It's just, there are all these little detailed things that, you know, like I didn't really ever think about because I was really focused on the warming mat, that I got to learn about when I was talking to her, talk about like, okay, if you guys are solving this, then I still need to do XYZ. So having the person at the helm to steer the barge is huge, and absolutely critical. And that person, like the fact that her job was just to, you know, I mean, she had, of course, she's a medical doctor too. So I shouldn't like be like, this was her only job, but just having her, you know, that be her focus, and then delegating like kind of who's doing what made it, I really think led to like the success of this. You know, she kind of knew what she wanted. She knew how that we needed to get there and kind of gave us a target. So.
Yeah, that's amazing. And yeah, and despite her, I'm sure there are lots of roles that she had as an individual contributor, but
yeah,
that primary function of being captain of the ship,
exactly,
so to speak.
Yeah.
So
I kind of like to think of it as a bard, mostly because it takes so much time to like turn, because it's such a big thing.
All right.
But yeah, but yes, captain of the ship for sure.
Slow moving ship.
Yep.
That is amazing. And I love the interdisciplinary team advice. And one thing that I would encourage folks to think about is, you know, what is your proximity to those people, right? And obviously in today's age, that might mean digital proximity. It may not mean physical, but one of the things that we got a lot out of the cyclotron road program being at LBL was you know, yeah, there were a lot of rules that were not ideal being under someone else's roof, but you know, okay, my team is sitting on, you know, the 4th floor of the molecular foundry, and there's all these other people working on really cool things that, you know, so the peripheral learning and the possibility to kind of have your team, I think especially for people with a small team, right? I think we, you know, we learned a lot more as a team than we would have like, okay, the 3 of us are all going to sit in a garage and just, you know, stare at each other all day, right? So I would definitely add to your, you know, the diversity piece is one, right? But then it's also like, what's the means to achieve diversity? And I think one of the really important things is getting yourself into, you know, speaking distance, so to speak, of a diverse group. And that might, you know, that might mean, I don't know, moving to a city where more people are doing what you're doing, or, you know, in today's, you know, everyone went virtual, you know, might just be joining groups or reaching out to people online, or
I like I really like what like Danielle said during her interview when she was talking about synthesis, right? Where she's like, I take a bit of, from this conversation and this conversation, and then like your brain subconsciously kind of takes these bits and pieces and like, I don't know, finds the solution, right? Like kind of combines them. And so I think that's like being in a diverse group, right? Like you said, on this fourth floor with all these other people, right? Having conversations about like nothing about, right, that is so
Yeah.
far outside your expertise. Like originally, at least for me, it was intimidating, but then like I learned so much about PCMs, right? And then as I was thinking about like the molecular structure of like what it takes to get something to change phase, right, at a certain temperature, like some of that actually applies to, I mean, at the end of the day, combustion is chemistry. So all things connect. And if you can get, the more information you get, even though it seems like it might not be relevant, it actually might be really relevant. So it's really good to get out there and I don't know, to not, not to emulate Steve Blank, but in a different way, right? Get out of the building, right? Get out of your garage, go talk to people, talk to them about anything, art, whatever. I mean, the more information that your brain like receives, the more you'll have to work with to solve your own problems. So
That's beautiful. Awesome. So let's we've got a couple questions, and I want to start with one that might take us a little bit to your other work, but we've got a question from Mark, who is a solar guy and one of the finalists actually of our Polyspectrum Revolvers Make It Real 3D printing challenge. So we're helping him on a solar idea. So his question is, have you seen thermovoltaics or thermoelectrics integrated into combustion system or cook stoves, or self-powering lower temperature devices like the baby blankets? So I guess my understanding is not just using an external thing to heat the phase change material, but having a thermovoltaic or thermoelectric material. Any thoughts on that?
yeah, so I guess it just with regard to thermal voltaics and thermoelectrics integrated into combustion systems, my short answer is yes. I have seen both of those integrated into like combustion devices or combustion systems. The success of them is varying for varying reasons. Because there's lots, as you can imagine, there's lots of challenges, right? Combustion's hot, it's a harsh environment. Thermoelectrics need a specific temperature. Thermal voltaics would like a constant, really high temperature. Yeah, it's a fun problem to solve because like you can't have your cake and eat it too. There's always like a sacrifice that you have to make somewhere. So you have to figure out what's the sacrifice. And of course, you don't want to sacrifice anything. Like, is it heat or is it emissions? And like, you can't have, it's really hard to have both unless you change the chemistry. And then the question becomes, well, like, how do you, if you want like better emissions, then how do you get the right gases, right? So there's always something fun there. I have seen thermoelectrics integrated in cook stoves. It's actually pretty common. I think BioLite is the biggest success story with that. They have, you can actually buy their stoves at REI because I think their model was to sell to like industrial country consumers and then use some of that profit to help developing countries with better cook stoves. And their stoves work well and they integrate a thermoelectric generator. With regard to using them for the baby blanket, I think it's hard because it's not reliable, right? Like in the sense of if you used some solar method, because I've seen solar cookers implemented. What if it's a cloudy day, right? What if it doesn't get hot enough or too hot, right? We don't want to melt the plastics, things like that. With a thermoelectric, I guess that one seems a little challenging because I guess you'd need the cold side. So I don't know how you'd get that to work with a blanket, but I'm open to suggestions. Like it's an interesting problem. So I haven't seen either of those integrated with the baby blanket. Boiling water seemed pretty simple. So that's kind of what we stuck with. Will say there is a company called Embrace that also makes an infant warmer that also uses a phase change material. Theirs is electric. So I don't know. I think they just run like an electric wire or something through it. So you plug it in and then it melts all of the wax. They had some success, and oh man, I hope I get this right. If I get this wrong, they're probably going to email me and be like, "You're totally wrong." I think GE bought them out, and then I don't think they've gotten anywhere after that. I don't think GE helped push it forward. So, so that's one technology that it looked really promising, but I think it's kind of stalled. I haven't seen it move forward. The other challenge with that was I think it's $250 for their device, and it needs electricity. So that causes some challenges as well.
Different design criteria.
Yeah. So that's the only thing I would say that I've seen that's closer to like using, where you could connect like a thermoelectric generator, thermoelectric device to like a mat to warm it. So.
Okay.
Hope that answers that question.
Yeah. I think that was a fantastic answer. Thank you. So I have a question for you, and I love your framing of, let's call them problem solvers, right?
All right. Yeah.
Obviously there's been a lot of advice over the course of this talk, but is there any specific advice that you'd have to a young aspiring problem solver?
Yes. So I actually I did a women in STEM video for DOE recently for high schoolers, and interestingly enough, I got like a few young freshman college women emailing me asking me like, hey, can I interview for some advice on this? Okay. And the advice that I give them, which I think is probably not the advice that most people give, is like, just like get through classes, right? Don't worry about getting the A, like just worry more about like, trying to learn the material, trying to understand it. Cause I feel like a lot of times when you're in undergraduate, there was someone I was talking to who was like, your focus tends to be like lab 4 hours, class, 1 hour, homework assignment 3 hours, right? Like you don't think about necessarily the material itself when you're first starting. It's more just like, how do I get through this? Mm-hmm. And so I think, shifting your focus on like, to be the smartest or whatever, I have to get the A. That's absolutely like not true. Just get through the material, get through the classes. You'll learn it as you go. And then just keep pushing forward, keep persevering. Don't give up. Right. The story I tell them is when I was a freshman, I hated physics, like legitimately hated physics. I struggled so hard. Like for me, the idea of like, my goal for myself was like, if I get a B- in this class, I'm gonna go celebrate, because that's probably the best I could do. And this was like general, like physics for engineering. It's the very first engineering or physics class where it's like, cannonball, you have to figure out the equation for cannonballs, right? Projectiles. And like, if you're in a sled and the friction coefficient of the snow is whatever, like how far will you slide an angle, right? Like for some reason that just didn't click with me. And that's year one, right? Like I was so incredibly frustrated, but I loved math. And I remember talking to someone and telling them, oh, I really hate physics. And he goes, well, you're never going to make it as a mechanical engineer. And like, much like Danielle, I don't like being told no. So I felt like that for me, that was a driver. Whereas I could see that being really discouraging for some. I got through the first physics. I got to the second physics, which was electromagnetism, which I loved because it was more math related. And then when I took statics and dynamics as a mechanical engineer, I learned that was the first physics course, and it totally made sense. And I realized that it wasn't the material that I didn't understand. It was the way the material was presented. And so the more ways that you can come at, like, this is where I feel like it's a real challenge for teachers, right? Like there's so many different learning styles, and to try and accommodate all of them is just like impossible. So as a learner, I think the more different ways you can try to tackle this to try and learn how a system works, the better. And that there is no one way to do it. So, you may not get the A, and it's okay. Just learn what you can and get through it. And if you're passionate about it and you really want to do it, just like, don't give up and keep going. So that's my advice.
Yeah, and hang in there. Yeah, and I think that's something that I'm trying to remember whose quote this is. It might be Seth Godin quote, but he says, we talk a lot about learning deficiencies, but we never talk about teaching deficiencies.
Yeah. Oh
And
my gosh, yeah.
Yeah, and I'll just share I had a very similar experience with physics in undergrad, because I was at Princeton, and Princeton is, like, if not the top physics department of the last 200 years, it's like
Right.
one or two.
Only slightly intimidating,
Yeah, well, and and so the graduate level research is like top notch, but the corollary to that is, even though Princeton in many other ways is incredibly focused on undergrads, for physics, the curriculum is effectively designed to go from about 115 kids who freshman year say they want to do physics to 12 who graduate. And it's purposefully meant to basically show you as quickly as possible that you're not going to be a physicist major.
Yeah. To me, that's a detriment.
And it's a bummer, because I very quickly, I was thinking physics or chemistry. I wasn't really sure, and physics was just so unpleasant in those intro, freshman year ones, that I kind of went all in on chemistry. And then later in grad school, I ended up working in between a synthetic chemistry group and applied physics group, and now I love it. And and now totally different experience. So and I guess the second piece I would just want to resonate with and share with folks is, and again, maybe this was not a good career move plan, but I'll just share my experience of, like, when I was an undergrad, I basically said, my top priority is like learning things that are interesting to me and that I think I can use in the future, not the grade that I get on this. And so I had a very low GPA in undergrad because I just was like, great, I'm going to take more math than is required. I'm going to take the real quantum mechanics course, not the one that the kids who want to go to med school take. I got a C in organic chemistry, and then I got a PhD in organic chemistry later. So it just like, don't let the grades get you down. And I think the grades say more about the teaching deficiencies than the learning deficiencies.
Yeah. And to add to that, like, as a PhD, how often have you gotten asked what your GPA is? Right. And then also, like, one of my best friends is an ER doctor, right? And I remember hearing about like the GPAs in med school. Do you ever ask your doctor what their GPA is? Right. Like, I just feel like I know it has value. It shouldn't be the top priority. So
yeah. Some form of feedback and evaluation is important, but
exactly.
Yeah. Okay. Well, don't let the grades get you down. Stay strong. I think that's really good universal advice. So yeah, I think with that view, I think we'll start to wrap it up. I really appreciate your time. I want to kind of end with just one final logistical question. I think, I've learned so much from you, and I'm sure a lot of the folks live right now would love to learn more about you and what you do. And so where's the best place for people to find out more about you, and how would you like to be connected with for those that want to reach out and learn more?
Yeah, sure. So all of my information in one place is on my website, so vhrapp.com. And the best way to reach out to me is probably via LinkedIn, which I think is vhrapp, or you can do Twitter. It's kind of hit or miss. I'm not really a tweeter. I'm really trying, but it's at v_rapp.
Okay, that's amazing. All right. Well, hey, thank you so much for your time today. I really appreciate it. Learned a lot and had so much fun.
Yeah, me too. Thank you. This is an honor.
Yeah. All right. Thank you again. Bye, everybody.
Bye.